down some animations and chat rooms, etc. Okay, Bernoulli's theorem, why do airplanes stall, why do golf balls travel further? There's lots of interesting things they found. So I'd encourage you to look at this page and give any feedback to the team who created it. To give feedback, this is feedback down here, feedback on this early page. So presumably you click there and you can give some comments. I get to do the feedback that we do. Okay, so there we are. You can have a look at that and see what interesting things there are there. It includes things like some lecture notes which have been typed up by students and some exercise and things. Okay. It also records this lecture. The ability to posterity. Okay, so let's get rid of this and make a start on the last topic. So, this chapter 7, I have to whiz through it in 3 lectures, so it's about 12 pages of my notes, so, or less actually, so hopefully we're okay. Okay, so 7 is boundary layers. And essentially we've already met some of these ideas because we've done a number of examples which had this concept involved. So one example which is one you'll know from the problem we've just been doing was the oscillating boundary. Essentially all the disturbance was in a layer of width and delta, which basically was roughly equal to root, what was it, mu over n. So we're also in the boundary. We had a thin layer where you get all the activity occurring. We also had an example of boundary layer last time where we did this problem involving the stagnation point flow. And again, all the actual boundary. Well, the boundary is only important, really, the thin layer. There was some kind of width delta which appeared in the calculations. Okay? Now, how to define, there's some kind of width delta. And finally, we had the Rayleigh problem when we started the boundary moving. With some velocity u, we had the fluid basically only moving in some region near the boundary. And the region here, delta, basically went like root 4 ut. So this increased like the square root of time. So again, outside this thin layer, the fluid is essentially undisturbed. You've got no knowledge of the boundary. Okay, so boundary layers already appeared in various questions, problems we've been doing. Okay, so let's and the key aspect we'll look at today, is the idea of flow around the body. Let me draw a picture of this. Suppose you've got some body, it's got some sort of scale L. Not being too definite what it means, it could be meters or centimeters or it could be islands or kilometers. And you've got some flow that's coming at it from a long, long way, with velocity capital U. In fact, it's a bit like some of the problems we did with Frank Quasar last year with flow around cylinders. But in Frank's course, there's no viscosity, whereas this course involves viscosity. So what if viscosity is very, very, very small in some sense? We essentially expect that the flow here won't really notice the body, it'll just sort of flow around it without too much going on. And you get with a very thin layer here, where viscosity is important. Looks like the examples over there. So viscosity is important here in enforcing your no slip condition. Okay. But some distance away, out here somewhere, essentially the flow doesn't really know much about viscosity, it just knows that it's got to go around the body. Okay. And the idea is you have basically a thin layer where you bring in viscous terms. Okay. Let me now try to explain this in words. Okay, so picture 7.1 is theory, because the diagram goes with that section. So for a, let's say, flow towards infinity, let's say. Okay, so, whoops. So little u is the whole flow field, big U is the kind of flow you've got coming for a long distance. Okay. And for flow, going past the body of typical scale capital L, we may construct a dimensionless quantity which is called Reynolds number. R is big U times L over mu. So if people are interested in why you get this coming out, then essentially U has dimensions length and time. So this is the quantity, these are dimensions. So velocity is in meters per second or kilometers per hour, whatever you like. Okay. And length L, the size of the body's got dimensions curly L. And viscosity, all of this is viscosity, this new thing, but it turns out if you track back through various equations, the dimensions of viscosity mu are L squared over T. Okay, so using nice curly letters, we're just measuring dimensions of quantities. So you take u times L divided by mu, and you get a dimensionless quantity. So it's independent of the units you use to measure the u, the L, and the mu. Okay. So for example, when you measure u, well, let's say L, if you measure L in meters, it might sound not very big, 0.1 meter. You can measure it in millimeters, and it sounds quite big, 100 millimeters. They're the same actual measurements. So the actual dimensional numbers don't really mean very much. It's only when you put them together in quantities that don't depend on how you measure them, you really get something useful coming out. Okay, so we make up such a dimensionless quantity called the Reynolds number, and that essentially tells you how important viscosity is. Okay, we're trying to measure how big mu is in some sense. Okay, this is quantity that called the Reynolds number. And it's the most important number in fluid mechanics. The first number you grasp for which will solve a problem. Okay, so when R is very, very big, so in other words, mu is much, much less than u times L, then we're in a regime where, in some sense, viscosity is unimportant. It's not important everywhere, it's only important in some thin layer around the body. Okay. So when R is much bigger than 1, viscosity is generally unimportant. Except in thin boundary layers. Adjacent to the body. And the downstream wake. Okay, so I'm going to pitch in a second. Okay, so what's the story? So, we draw a picture. Got some flow u, capital U coming from infinity. Got our body here. Essentially the flow goes around the body and you have this thin layer where the flow adjusts. On the actual body you've got no slip, then it adjusts rapidly to the flow past the body and then there's slip to the actual fluid velocity. And you have that sort of thin layer. This is the boundary layer. Okay, so I use the L for boundary layer, it's handy. deviation. And then what tends to happen behind the body is often this boundary kind of peels off. So you actually end up with this kind of behaviour happening. And behind you get all sorts of complicated motions. That's called a wake of the body. If you like, think of a ship going through the water. There's a ship. You sit in the front of the ship, which is the stern on the ships. And you watch the water flow past, then you look behind the ship, there's a great wake of waves and turbulence going so well. Well, you can't see it actually, this is where I can now reach for this nice page, because it flows, let me do it here. Just see. Yeah, flow past the body here. It's just a cylinder flow, and the fluid flow's gone around the cylinder. You can sort of see a wake here behind the cylinder, and that's where they're getting complicated motions, which in this case turns into a volcan streets where you have vortices peeling off, making an interesting regular trail behind it. Oops. And you can usually sort of whiz around all the different movies, can't you? Whether music ones or scientific ones. Here's flow past some other body. And again, you've got sort of flow going past the body and then it's peeling off to create a sort of wake behind. And then, depending on what the Reynolds number is, this wake will be very simple or get more and more complicated. Yeah, leave it for a second. We'll probably turn it the Reynolds number now, make it more interesting. Or not. Anyway, that's the point. You get something sort of interesting occurs behind the body. And that's going to be also gets complicated, it's very hard to analyse. This is probably turning up the Reynolds number to make it more interesting flows. I used to create on Carmen Street with these vortices. I guess the blue and red body vorticity peeling off. Of course, this is fantastically hard to analyse, and what's the solve problems here for fluid mechanics where you can really look at numerically. We're just going to focus on the basics of sort of the boundary layers you get in native bodies. Okay, so let's then try and get some actual theory for very simple problems. Having talked about some of the, I've seen some pictures. So what's the key approximation? What's the key approximation here? The key approximation is basically just a very thin layer. Okay. So the basic I don't call write B out of boundary there. Okay, boundary approximation is to neglect diffusion of vorticity parallel to the boundary. So if you like look at the boundary here, and you've got a thin layer, and basically you're including diffusion going this way, but not diffusion going this way. Okay, so this is the sort of approximation. Let's have a look. So if you have to, so here basically we're comparing mu d2 omega by dx squared divided by mu d2 omega by dy squared. Those are the two terms we've got. So this is basically diffusion. Let me draw a. This is still in the relevant picture here. We've got some coordinate x this way and some coordinate y going that way. Okay, a bit curved that picture, but you can imagine it being straight as well. It doesn't matter too much. Essentially, basically, we neglect. Well, this one basically is diffusion parallel to boundary. This is diffusion perpendicular. Okay. And if a terms, this basically is equal to, of the order of omega times mu over L squared, divided by order of omega times mu over delta squared. So the scale of the body is capital L, and the scale of the thin layer is scale delta. Okay. This is equal to order of delta squared over L squared, which is small. Delta is small and L. Now I'll say some words in a second. Just going to throw away the first term. Okay. Okay, so here delta is the width of the boundary layer, like in other examples, and so here delta is equal to the width of the boundary layer which is taken to be much less than L, which is much smaller than scale of the body. Okay. Scale capital L of the body. So let's put that into the equation. So we've got the vorticity equation. We've been doing this in various bits of the course. So we have the vorticity equation. So U, it's the omega by dt plus U d omega by dx plus V d omega by dy is equal to mu d2 omega by dx squared plus d2 omega by dy squared. That's the vorticity equation which we're deriving in sheet 3. That's how we're deriving in sheet 3, question 2. Okay, just going to do. So the key approximation is basically throw away neglect this term. Key approximation. And we'll take the equation steady as well. So we'll assume steady flow. We'll take examples with steady flow. It's not quite the right form. This was filled with a little bit further to a nice form, and then we can do some problems involving this. So today basically says looking at the sort of background theory, and then we'll actually do a problem tomorrow. So basically we're going to put an equation which is standard boundary layer equation, and then we're all set. And we can look for some similar type solution like what we've been doing recently in the problem sheets. Okay, what else can we do? We've made this approximation here, we've simplified this. So also, we have that omega is equal to minus del squared psi, which is minus d2 psi by the x squared, minus d2 psi by the y squared, and that comes about when we have a stream function. So we have this, if you recall, u is equal to d psi by dy minus d psi by dx 0 into d. All this 2D with no vertical flow. And when you do the curl, you get that. Okay. In a similar spirit, we're going to neglect this term. So we're neglecting essentially these x derivatives by comparison with y derivatives. So basically, in the same spirit, we neglect this term. I'll say it in words in a second. Which where are we? Okay. So here we neglect d2 psi by the x squared in comparison. Oops. D2 psi by the y squared. Because things very much faster in the y direction. So let's then go and plug everything into this equation, and we'll get something. This is a whole mess. That will be revealed as something we actually isn't too difficult or unfamiliar. Okay, so with this asterisk becomes, let me label this thing as asterisk. So what do we get here? So it comes with a mess. U is d psi by dy, and omega is minus d2 psi by dy squared. So we get minus d3 psi by the x dy squared. Or are you just thinking, look, sympathise. Okay, so that's the first term. And then we get plus, got v the omega dy, and that turns into psi dx d3 psi by dy cubed. That's the left-hand side sorted out. And then the right-hand side we get equals minus mu d4 psi by dy to the 4. It gives me probably looking equation. This sort of, well, we'll see it turns something we do understand in a minute, so it's particularly horrible, it's not. Something we just remember, it's just a derivation. Or if you prefer, so let's, if you prefer, you could make it a bit less unpleasant by using subscripts. So it's minus psi y, psi x y y, plus psi x, psi y y y, minus mu psi y y y y, y y y y. Okay. Y y. Not quite so bad, does it? Okay, anyway, what's the point here? This could basically be integrated once with respect to y. And this is just sort of pulled out of the hat from our point of view, which is fine. Written as it's minus psi y, psi x y, plus psi x, psi y y, is minus mu psi y y y, plus psi g x over the check by differentiating. So if you take this line, so let's use to differentiate the integrate. So you take this line here, you differentiate with respect to y. What you get? Let's just do this. Slide from the camera's running. Differentiate. You get psi y, psi x y y for the first term minus psi y y, psi x y. That's the first term differentiated. And you get plus psi x, psi y y y, plus psi x y, psi y y on the left hand side. And lo and behold, two terms cancel. And you get back to what the left hand side is above. And of course, you differentiate the right hand side minus mu psi y plus 0 because g is just dependent on x. Okay, so basically you end up with that. Okay, hopefully I'm nearly finished with this because it's a bit painful. Yeah. So you can integrate this one with respect to y to give you this line here. And this basically is a constant integration that could depend on x. And basically our pressure gradient again. So we leave it back to nanostics. This is let's put it here. So here g of x is a constant integration. Which could depend on x. Common function of x. There's a constant with respect to y because the whole x constant differential. Okay, anyway, so we get down to this line here. So what is this talking about? This actually is the Navier-Stokes equation back again in some form. We can hopefully see that and make sense of it. Okay, so this in fact is the x component of the Navier-Stokes equation. Which is so u is psi y and v is minus psi x. So the first term is minus u du by dx. That u is psi y and psi yx. Psi xy is u by dx of u. Okay. Then again minus v, which is the psi x here, and I get d by dy of u. That's not too bad, inconsistent signs. Is equal to minus mu. Sorry, I get minus mu d2 by dy squared. Okay, so the signs are right, it's just consistently minus sign into it, which is sort of good. by dx plus mu dt u by dy squared. And that's basically part of our Navier-Stokes equation. Okay. So let's make various notes. First of all, let's stick over here. So recall Navier-Stokes is du by dt plus u dot grad u minus grad p over rho plus mu del squared u. What I'm doing here is taking the x component of this. So this bit comes from mu dot grad u. It's all steady, so that isn't there. I've got the exponents of grad p, and I've got mu del squared u, and I've thrown away the d2 by dx squared. And this basic equation is solving boundary layer theory. Okay, so let's make a few notes on those lines, and then we'll chat and we'll give up today. So here basically, just some bullet points. So this is the x component of the Navier-Stokes equation. And it's steady, so the u by dt can be replaced by 0. And we've neglected d2 by dx squared. Which is what's this in del squared u. And the other key thing is this g of x business. So when we did this, we got this g of x, which was the same as this term here. And essentially, it's here if you like. It only depends on x, it doesn't depend on y. Okay. So the pressure gradient piece here, which was this, with minus sign, so 2 cases of that, doesn't depend on y. Okay. So key point is the pressure gradient term. So it's dp by dx is big G of x up to plus minus sign. I'm just slightly different from what I'm saying. But it doesn't really matter whether it's plus sign or minus sign. The point is it doesn't depend on y. Which is rather important. We'll see what we're doing. Right, so that's what we've got. So that's basically the end of this sort of bit of analysis. This is the key equation for solving in all these kinds of problems. And it has been simplified with these 2 key points. Thrown away correct derivatives on the right side, and the pressure is a bit simpler than we might otherwise have. Okay, so probably what's really going on here, and how to actually make some sense of how you use this equation. Okay. So last sort of 10 minutes, let's just outline that and then we'll do an example tomorrow. Okay, so just follow this key point here. kind of give a flavour of what's happening here. Let's see. So here's my boundary. I've got y this way. Don't care too much which bit of the flow this is. We've got some flow coming past, and there's a sort of thin layer in which the flow is adjusting to the no-slip condition. So you sort of draw a line here, dashed line if you like, somewhere. And this is basically some sort of width delta. Outside this layer, the flow doesn't really care too much about the boundary. So it doesn't care much about the no-slip condition. So you've got some flow up here, which is basically going past the body. And then inside the layer, essentially coming back to the no-slip condition. So here, on the actual boundary, u equals naught no-slip. What's the idea? We might just solve the problem without thinking about viscosity. So you sort of solve the problem up here, with flow past some boundary, and you do the kind of stuff in Frank's course, and neglect viscosity. And you call this bit up here the mainstream solution, if you like. And here you neglect viscosity. And you set about solving sort of momentum of the fluid and all the forces that are there, throwing away any reference to viscosity. And that will then fix some sort of pressure gradient. So it fixes P, the pressure, which would depend on X and Y, up here. Okay. And then you come and solve with the boundary there. So now you see, actually, you're homing now this region here, and now you solve what's happening here. And essentially the pressure you get out here gives the pressure you need to solve this problem. So here we use the P, you sort of X from 0, because you're looking at Y coming down. Well, X, let's say P of X and Y for small y. So you look at what happens outside, you come in towards the layer to solve here with viscosity. Okay, so that's the idea. So the P comes from elsewhere. Let's write that down, then we'll that's some form. Okay, so there we go. Pressure is determined by the flow outside the boundary there. So let's carry on with this. So this is the main stream flow. In which viscosity may be reflected. Okay, and here the values of y have got what you call order 1. They're kind of values that are not particularly small. Okay, then a pressure distribution P along the boundary so here would be P of X and Y for small y is plugged into the equation of the boundary there. Which in fact is this one here. So essentially when you get to solve this equation here, you kind of know what dp by dx is. So final comment. So if you look at this equation and imagine you're heading upwards at the boundary there, then essentially you're losing the effective viscosity, and also this term is becoming unimportant. So if we increase y from scales or delta, we leave the boundary there, so we leave the effects of viscosity. And our bound layer equation becomes u by dx minus 1 over rho d by dx. I'm also neglecting, you can show you're neglecting the du by dy term. Okay, well, if you integrate this, give you half u squared plus p over rho equal constant. So integration with respect to x gives you that. This is called Bernoulli's theorem, which thinks the flow up here somewhere to the pressure. Okay. This looks the flow outside. Outside out there. To pressure P. Let's call Bernoulli's theorem. Right. Basically, I'm going to stop there. It's been a sort of bit of a rattle through the theory here. Next time we'll basically get some more complicated examples and sort of see how to work it in practice. This is the last topic in the course, the last topic. We'll go to about 3 minutes on this and so I'll stop there. I've got sheet 4, sorry, yeah,